Okay, so hopefully you guys are working on your current assignment. As we discussed, you'll be completing the university application. Okay, and of course you will be adding more classes. Okay, so now how to submit the assignments. Okay, I remember on the website there's already a URL for, I forgot, it was like CS440 fall 2015, is that right?
Yes.
At yahoo.com. Okay, so anyway, so what you will do is you will zip your project, and you will also add a small Word document with screenshots. And so this does not have to be too big, you know, just a few pages or one page, depending upon how complex the assignment is. Okay, and you should also mention the status of your assignment, completely working, or there are some errors, okay, or you know, partially working. Okay, if you did any enhancements, so for example, if you went beyond the requirements and you did some extra enhancements, so make sure you mention those so that the graduate assistant can appropriately grade it and give you the due credit. So anyway, so put the Word document and also your source code. So this will go as a zip file, and then send it to, and once you send the zip file, you know, sometimes you simply will say, the file name will say assignment1.zip. So my suggestion is also name the file so that you could be easily identified. So if you can also, instead of like this, if you can say assignment1 underscore your ID, whatever, 983526 underscore, you know, whatever your name is, okay, .zip. Okay, so this way it would be easy for us to track who submitted the assignment, what date it was submitted, and so on. Okay. Any questions on the current assignment? Everybody feels comfortable with the keywords that we discussed. So as far as object-oriented programming is concerned, remember we said encapsulation is one of the key ideas, and this is easy. This is basically creating classes. And once we create a class, of course, we have private keyword, we have public keyword, we have protected keyword, right? So hopefully everybody understands. Both the data as well as the functions as well as the class itself could be marked private or public, okay? So if you create a class XYZ, okay, if you declared some, let's say, string first name, okay, and somewhere over here you have something, let's say public double, let's say compute pay, right? Okay, so as far as data is concerned, meaning the variables inside the class, what is the best practice from object-oriented point of view? Keep it private or public? Private, right? And the default is private anyway, so that even if we don't write, it will be private, right? Any method that we write, remember method is another name for a function inside a class. Okay, functions will be usually public, right? Okay, sometimes If we don't want this to be available outside of the class, we will mark it as the function also as private, okay? But most of the time, the data will be private inside the class, and the functions will be public, right? When do we mark this as protected?
When it has to be accessed outside of.
So if there was a derived class, for example, we created another class called, let's say, manager, and it inherits from XYZ, right? And somewhere over here, we have some function, let's pretend, and this function wanted to access the first name. So if it was marked private, okay, then obviously we will not be able to read this data over here. So that's the time this will be protected so that the derived class can easily access it, right? So again, these are basic object-oriented concepts. So all of these concepts of private, public, protected are part in creating the class itself, are part of the encapsulation idea, okay? Now, as I mentioned briefly, the class itself can be marked private or public, but not protected, okay? So why do we want them mark the class private or public? Even if we don't mark anything, what will be the default visibility of this class? Private, okay? So again, so at the class level, what does private, public mean? See, at the data level, at the function level, it makes sense that from the outside of the function, can we call this, can we access this data? But what about the class itself, okay? See, when you create a project, in a project you'll be creating many classes, right? For example, let's take a look at our university assignment. You are creating student, grad student, and so on, right? So all these classes, however many you create, right? They are compiled, and once they get compiled, they go into a single file, okay? Which is the exe, executable file, or sometimes if we compile it as a library, it could be in a DLL file, right? So the compiled code will go into a single file, exe or DLL, depending upon how we compile it. So far, everything we are doing, we are creating a project, so it will go as an exe file. So that compiled file is also called the assembly. Okay, so sometimes, as our projects get bigger and bigger, we create many assemblies inside of our project, meaning there could be many executables or DLLs in our project. Okay, so let's say this is one project, here's another project, okay, which is part of a bigger project. So what if it wanted to access and create an object of this class? So create an object of a class which is declared in a different assembly, okay? So if it was marked private, what will happen? Will we be able to create this object of this class in a different project or a different assembly? No. Okay, so that's why at the class level also we have private and public, and gradually as we make as I show you how to create DLLs and bigger projects, then we'll worry about this part. Okay, for right now, all classes within the project, so all classes within the project, they can see each other because they are part of the same project. So even with the private or no keyword over here, it's perfectly okay. However, outside the project, these classes will not be available. Okay. Okay, so now let's go, where's the eraser? So now let's go to the second concept over here in object-oriented programming, basic object-oriented programming. That's what we are reviewing right now. Okay, next concept was inheritance, right? So as you guys saw from the last example, inheritance only makes sense when many classes are involved. Right? If you created a project with a single class, then obviously there's no inheritance. So Purpose of inheritance, as you saw, was to write less code, right? Okay, in the technical terminology, we also say or to promote code reuse. Okay. So because if we are creating a large project, the less code we have, overall less code, the easier it is to maintain, easier it is even to create the whole thing, right? So that's where we discussed that in the beginning, nobody knows what classes to create, how the inheritance will work. We all gradually discover ourselves, refactor the code, meaning readjust the hierarchy of the classes and their relationship. So hopefully through this example, you guys saw what was the starting point. If you are given a new project to create, the starting point will always be what are the real classes or real entities that exist in real life, okay? So for example, if you're creating a university project, it's the undergraduate students, grad students, PhD students, part-time students, those are the ones that exist, right? For example, let's say if you're creating a human resources application, right? Then where will you start? Okay, again, you will try to identify for whatever organization you are creating the HR application for. What are the different types of employees? Because purpose of HR is to coordinate all the employees. What are the different types of employees that exist, right? So starting from, let's say this is a technical organization. There might be, for example, a programmer as one of the jobs. There might be senior developer. There might be a project manager, right? There might be a vice president of a division, right? And so on. So basically, once you've identified these are the actual people that work in the organization and these are the categories or their titles, then you'll start creating classes for each one of these. And then pretty soon you'll discover you're repeating things and you'll move them to the base class, right? Okay, so after we are done with inheritance, one of the keywords that we run into, as you guys saw over here, so some of the keywords that we run into were abstract, right? So if we created two classes representing some real entity, then we discovered there were a few common things between in those classes. And we moved those common things into a base class. Okay, how will you declare this base class itself overall? Abstract. Regardless there's real code in it or there's no real code in it, it doesn't matter, okay? Because in real life we will not be creating an object of this class, only these are the things that exist in real life. So this was created strictly to reuse the code. So all higher level classes are generally marked abstract, okay? Unless you can see a reason to create an object of it, which, like I said, is rarely the case, okay? So we saw keywords of abstract, virtual, and override. Okay, those were the three important keywords over here. Okay, then related to classes, not necessarily related to inheritance, we had one more keyword called static. Okay, and remember the reason we create a static is if there's a class XYZ as an example, suppose it has some data. Okay, suppose we have some function, let's say compute. Okay, and the compute, it may take parameters, it may not take parameters, okay? But the code inside the compute never uses any data inside the class, okay? So that's the time to make the caller's life easy, so that the caller does not have to create xyz x1 equals new xyz, and then x1 dot compute. See, if this was not marked static, then the caller will have to write some code like this, right? Okay, so to make the caller's life easy, what we do is, if we recognize the code is totally self-contained code, once again, what do we mean by that? Meaning it never uses the data inside the class, okay? It either uses the parameters that are passed to it, or creates its own local variables, and based on that, it does some computation, right? So if it is a self-contained code, that's the time we can mark it static. Okay, so once it's marked static, then how do we call it? Name of the class dot name of the function. So the calling code becomes a lot more easier. That's why we mark a particular method static inside. Okay, now even if the code here is using the data, okay, so suppose it does use this data over here to do some computation, then as long as the variable or the data is also marked static, then it's okay to use it inside. Because a static variable means there will be a single copy of that data no matter how many objects we create. So that will be a shared data, right? So bottom line is that we have to understand all these keywords, private, public, protected, static, abstract, virtual, override. So very briefly on these, when do we use abstract, when do we use override? Okay, so we already discussed if we are creating a base class, then this will be marked abstract, right? Okay, inside the base class, we can still have abstract methods, but not abstract data, okay? So suppose there was a function over here, there was a function over here. Okay, for example, if you remember when we were writing compute grade, okay? Let's pretend this is a undergraduate student. This is grad student, right? So over here, let's say the compute grade formula was 0.4 and 0.6 was the weight for the test 1, test 2. Okay, over here it was 0.5 and 0.5, let's say for the grad student. So once we move it to the base class, what code should we write? Should we write 0.4 or 0.6? And the answer is, it doesn't make sense now because we don't know whether the actual object will be undergraduate student or graduate student. So in fact, in this example, we will declare compute grade over here and will not put any code in it. Okay, so this is where we will mark it as abstract, right? Okay, now coming to the virtual and override, okay, if we have a base class, we have some method over here, we inherit one class from here, so this is the base class, this is the derived class. Okay, so now regardless, this was declared abstract over here. So if it was declared abstract, then there will be no code in it, right? It will be just one line declaration. So now if we wanted to inherit from it and provide real code for it, okay? So there is some code over here. So as we discussed, that's the time we will mark this method as override, right? Now what if in the base class there is real code over here? So it's not a single line code, there is a real code. We still wanted to inherit and change the code.
Virtual.
So then this has to be marked virtual, and this will be marked override, right? What if from this class we wanted to inherit another class? and further change the code. That's overriding. So that's when from an override we'll go further to an override. Okay. So let me briefly clarify this keyword virtual, because if you're coming from a C++ background, then it is the same as virtual in C++, but if you're coming from a Java background, there is no keyword called virtual in Java. So what does virtual mean? Okay, other than the fact that it allows somebody to override, okay, there is a significant meaning behind the keyword virtual. So let me explain what that means. Okay, so suppose we created a class. Okay, doesn't matter what it is, X, Y, Z. We declared some data, let's say int A, int B. Okay, and we may have some public get set property or methods, either way, get set over here, right? Okay, and now let's say we declared a method public, let's say double compute. Okay, so now let's pretend we created another class, let's say class myCompute. Okay, and it inherits from XYZ. Okay, and so we declared some data, let's say int C, and whatever the corresponding get set is. Okay, and then we wanted to override this, so we said public override double compute. And we wanted to provide some different code, whatever that code is, right? So that was the goal. Okay, so first of all, if we left it like this, you'll get a warning. Okay, the warning will be, because we are using an override, okay, and over here, remember it hasn't given the permission to override, right? So it will still run, but it will give you a warning. Okay, so let's try to understand again what that warning is and why do we need this virtual. Okay, so one of the rules in object-oriented programming for all languages, for all object-oriented languages, C++, Java, C#, and so on, is that a base class reference can point to a derived class object. Okay, so meaning, in this example, what's the base class? XYZ. What's the derived class? myCompute, right? So it is perfectly okay to create a reference, let's say XYZ X1. Remember, all class objects in C# are created on the heap. So if I say XYZ X1, does it create the memory for storing A and B?
Yeah.
No. It's just a pointer. It's just like, and that's what we call a reference. Okay? See, until I say new XYZ, only then the memory for storing A and B will be created. If we simply say XYZ X1, what will the computer do? Let's say here's the CPU. Okay, let's say here's the stack area. Here's the code area, and let's say here's the heap area, right? So if you don't see the new keyword, where's the memory allocated? Stack. So XYZ X1 basically will go over here, create what we call a reference x1. Okay, so think of x1 like a pointer to some area in memory, but right now it's pointing nowhere. Okay, so that's what we call a reference. Okay, so now later on we say x1 equal to new xyz. So now what will it do? As we have discussed before, anytime you see the new keyword, where will the memory come from? From the heap. From the heap. How much memory in this case? Memory for the data fields. So A and B will be allocated. And because we connected it to x1, so this x1 will be pointing over here, right? Now we can easily say x1 dot A equal to 5. So we can store, we'll start from x1, we can store 5 over here. We can say x1 dot b equal to 7, we can store 7 over here, right? Okay, what will happen if you forgot this line? So you do not have this line. Okay, will it give you a compiler error? Will Visual Studio show you squiggly lines when you are typing it? No. It will still work, but when you try to run it, what will happen? See, since we never did new xyz, does this exist?
No.
No. So x1 is pointing to nowhere. Now as you try to run it, it will do x1 dot A, but it's pointing nowhere, so you will get an error message, null pointer or null reference exception, something like this. Meaning this is pointing nowhere, or it is null. No memory was allocated, so there is no dot A that exists. Okay. So anyway, so to fix it, we can either do it like this: x1 equal to new xyz, right? And then it will allocate the memory for A and B, and this will point over here. So this will work. Or, as I have mentioned to you, the shortcut to writing these two statements is what? In the same line, we put new xyz. So once again, this is actually two statements. xyz, x1 creates the reference x1. New xyz allocates the memory and connects x1 to it. Okay? So anyway, now coming back to this concept over here, base class reference can point to a derived class object, right? So this is perfectly okay. However, according to this concept, we are saying that if we create a base class reference, it can point to an object of my compute. So somebody could, if they wanted to, say new my compute. Okay, so now how much memory will it create now? So again, break it in two parts. xyz, x1 will create this. Create this x1, correct? New my compute. So how much memory do we have over here?
C.
A, B is being inherited. C is being added. So 3 fields will be created over here. A, B, C. And because we say xyz, x1 equal to new my compute, they'll be pointing over here. Okay? So the question is, what about these get set functions? And what about this compute function? Where does that go? Does that also go with each and every object?
Code.
Okay, see, if we stored it with each and every object, so my compute also. Okay, does the code in my compute, let's say we were doing something simple. We were saying return A times B. Okay, here we were doing return A times B times C. Okay, pretend the public property was called A, and suppose I did not mark it protected, so the only way I can access here is through the public property, right? So no matter if I create x1 or if I create x2, okay, so suppose I create 2 of these, right? x1 looks like this, and suppose I was also storing the code for my compute over here with each and every object, okay? What will x2 look like? x2 will look like, again, there will be A, B, C, and, sorry, not my compute, I called it compute. So the code for compute. Code for compute. So together, okay, so what's the code in the compute? Isn't it, because we allocated memory for my compute class, the code for the compute method is A times B times C, right? So as you can see, whatever the assembly language equivalent of A times B times C is over here, it will also be A times B times C. Let's pretend it got expanded to 5 assembly language instructions once we compiled it, right? So what's the difference between these 5 assembly language instructions and these 5 assembly language instructions? Aren't they 100% the same? Right? So we'll be wasting memory if we keep storing with every object the code for the method also. Right? So that's why, and again, you can, what if this was, instead of 5 lines, there were a lot of code over here. Well, what if this was 5,000 instructions? Now we are repeating the same 5,000 instructions, storing them twice. What if instead of creating 2 objects, we were creating million objects of my compute? So million times 5 or whatever, 5,000, it will be a huge wastage of memory, right? So that's why whenever the compiler compiles the code, only the data is stored with each object. Only the data is stored with each object. So where does the code for all these get set as well as the compute, where does it go? It goes into a single area called the code area, okay? So over here, there will be code for set, code for get. Okay, so this is our code area. So this will be set A, get A, set B, get B, set C, get C, right? And what else? One more function called the compute. Right? Okay, so this will be for every class. So this is, for example, class my compute. Very similarly, there will be another code area over here for a class called XYZ, right? Okay, so now let's take a look and see, suppose we create, let me go back and only create one object. Okay, we created one object and connected it to some memory, right, ABC. Okay, so now what will happen if somebody, okay, let me remove this. Somebody tried to do this, double result equal to x1 dot compute. Okay, how will the computer know what to call? Okay, so remember there are 2 classes over here. There's a compute class over here. There's a my compute class over here. There's an XYZ class over here. Both of them have a compute function. Both of them have a compute function, right? So let me, so pretend our code area from here to here. There's more room over here. So there's also get A, set A, and so on, and there's also compute over here. Okay, now this part is for XYZ class, correct? And this was for my compute class. Okay, so there's a compute over here. So there's a compute method over here. So there's a compute over here. There's also a compute over here. So the question is, when we write x1.compute, which compute will be called? Will the compute belonging to my compute will be called, or the compute belonging to XYZ class will be called? Okay, so how does the computer decide, or how does the compiler generated code take us to the correct code. So here's the answer, okay? As we compile the code for this particular call, okay, what the compiler does, it checks what type is x1, okay? So it will go up above. See, anytime we are writing code, there's what's called the symbol table, which is maintained by the compiler. So every variable you declared in this symbol table, the compiler stores what data type it is. So for example, once we did x1, see, it doesn't look on the right-hand side, x1 is xyz. So it will say x1 belongs to xyz. Okay, so once the compiler is trying to translate this to the machine code or the assembly code, it will check x1 by going to the symbol table. What will it find? It's of type xyz. Then the compiler will go to the xyz class and see, is there a compute? Yes, there is a compute. Where was the compute for xyz stored? Let's pretend it was stored at some address 5000. Okay, so this will be replaced by call function at 5000, right? So that's how it will be able to call this function. Okay, now is that sorry, it will not call this function because this is xyz and xyz compute is over here. Let's pretend this is 3000. So it will say call function at 3000. Okay, so we'll end up calling this function over here in this example. Okay, why? So let me go over it again. Compiler will check what type is x1. It's xyz. It will go check, is there a compute? Yes, there is a compute. Where did it generate the code for storing compute? It generated the code at memory location 3000 because this is the xyz for compute. Let's pretend this is 5000, the compute for my compute class. So this will be replaced by call function at 3000, which is basically compute for xyz. So the question is the compiler doing the right thing? What type of object did we create over here? It was not XYZ. See, using this property of the object-oriented programming, we actually allocated my compute. So what was the goal of the programmer? The goal of the programmer was to call the compute in my compute, not in XYZ. So this is where the virtual keyword comes into play. So now if we go back and put the keyword virtual over here, okay? So let me show you how the compiler will be able to generate the correct code. So first let me show you slight more detail how the different classes are stored over here in the code area. So let me clean this up a little bit. Okay, so if I let's go make the memory a little bit bigger. Suppose this is the stack area, and suppose this is the code area. From here to here is the code area, and suppose this is the heap area. Okay, so let's go through the same scenario. X1, XYZ X1 will allocate X1, so we call this a reference. Okay, in C++ we will say XYZ star X1, so X1 will be a pointer, right? New my compute, as we discussed, will allocate how much memory? 3, A, B, C. Collectively, this will be pointing over here, right? Okay, see, we also need to maintain some connection from here to whatever methods belong to this class, okay? So in reality, there's one extra memory that is allocated over here, and that's called the vtable pointer, or the virtual table pointer. What is vtable? Vtable is basically a table of function pointers. Okay, so in the code area, there will be a vtable for every class. Vtable for XYZ class. There will be a vtable for my compute class. Okay, so whenever we create one object, we actually allocate one extra memory. We allocate memory for all the fields, and the extra memory is the vtable pointer. So because in this case we created new my compute, so this will be pointing to basically over here. Okay. Now, what does vtable itself contain? It contains, so let's go to my compute. How many functions do we have in the my compute class total? Okay, remember these get set are also functions. So as you can see, 2, 4 we inherited, 2 we added, 6 and 1 7. So there will be basically 7 entries over here. Okay, the first entry will be the code for, let's say, get 8. So whatever the actual code is, the compile code for, right? Very similarly, the last entry over here will be code for compute. Okay, so vtable is only generated if a class has one function that is marked virtual. If there was a class where we did not have any virtual keyword mark, vtable will not be generated. Okay. So anyway, coming back to over here, how does the so now let's pretend we do have virtual, we do have override. So how will the computer know which function to call, and it does not end up calling the wrong function? So this is what the compiler does. Checks x1. x1 is of type xyz. Goes to xyz. Is there a compute? Then it further checks. Is it marked virtual? If it is marked virtual, that basically means call the function through vtable or the virtual table pointer. Okay, so now the compiler will generate quite a bit of code. The code will start from x1. It will go to the actual object. It will go to the vtable. It will locate wherever is the pointer for code for compute. So anyway, then it will come over here and will be able to make the call. So it will be guaranteed now that the call will be made to whatever object we actually allocated, not the one this belongs to, but actually the memory that we allocated from. Because once we allocate the memory, the vtable will be pointing to this particular class and not the one that we created. So, so that's the idea behind the virtual keyword. And very briefly, what if we created one more class? Let's say class compute or my compute 2, and this inherits from my compute, and we did an override of the compute. Okay, and the caller did something like this. So let me change it now. Okay, so the caller did something like this. My compute MC equal to new my compute 2 and MC dot compute. So somebody is trying to call the compute through an object of my compute too, right? So the question is, which compute will it call? Will it call this compute? Or will it call the compute in compute 2 over here? Okay, so again, the way the computer will resolve this is, it will check what type is MC. MC is my compute. So we'll go to my compute and check, is this marked either as abstract or override or virtual? Because in all three cases, that means calls should be made through vtable, which is a table of pointers to the code for the function, each function, right? So what will it find? In this case, once it goes to my compute, it will find there's an override keyword. So it will not try to just directly call the compute for the my compute class. It will actually generate the code. So in this example, okay, remember there's a V table for XYZ, there's a V table for my compute, there's a V table for my compute too, right? Each one of these has all the pointers pointing to the real code for each function, right? Okay, and now if we did this my compute MC, what will happen? MC will be allocated, correct? New my compute 2, so suppose there's also an additional memory for D as an example. Okay, so how much memory will it allocate now? A, B, C, D. So it will allocate A, B, C, D, right? Is that all the memory it will allocate, or will it allocate one more
compute?
One more V table pointer. And where will that V table pointer be pointing to? To this one, right? And the last entry over here will point to the code for compute, for my compute 2 class, correct? Because this V table is for my compute 2, correct? Okay, so anyway, so now once the compiler is trying to generate the code for which function should be called, how will it generate that code? It will say start from MC. Okay, so first, of course, it will check compute. It will check MC. MC is my compute. So we'll come over here and we'll check, is it one of these 3 keywords? So sure, it is one of these 3 keywords. So then the compiler knows that it should not try to guess which function it should call. It should actually go to the actual object, locate the vtable pointer, and then call the function. So we'll start from MC, then it will come over here, then it will go over here, then it will locate the code for the my compute, and then whatever that code is, it will end up calling the compute for my compute, which is the right thing to do, right? So that's why we have these keywords, so that we can let the compiler know whether it should directly assume which function to call, or does it have to go through the vtable to call the function, okay? So all of these complications are needed because of this fact. If we did not have this need, then there's no need for a vtable. The compiler can simply check, oh, it is this type, let's call the compute in this class, okay? Whenever we have a base class reference pointing to some other class, some other derived class, that's when vtable is needed, okay? Okay, so now very briefly, how come Java does not have the virtual keyword? For those of you who have done Java programming, there is no virtual keyword in Java. Okay. Why C# gives us an option to use the virtual keyword or not use the virtual keyword. Okay. So the answer goes like this. Remember, if we did not use the virtual keyword, okay. For example, suppose I did something like this. So I created an object of my compute, and then I tried to call x1.compute. Okay, and I eliminate this virtual keyword. So even though I'll get a warning, I leave the warning, and this is the code I wrote. Which compute will be called over here if there is no virtual?
The direct plus one, because the
Will it
super
call
class
the my compute
Yes.
or XYZ compute?
is my compute.
They will call the base class compute. Because remember, so once again, if you are the compiler, this is how you decide. Okay, you check what is x1. It is XYZ. So you will actually go to the XYZ class and you will examine how is compute declared. If it does not use one of those three keywords, abstract, virtual, or override, that means there is no need for a vtable. Okay, so if this compute